Hi, I'm going to talk about angular momentum. So I googled the question what is angular momentum, and this is what Google told me. Angular momentum is a noun. It is the quantity of rotation of a body which is the product of its moment of inertia and its angular velocity. So angular momentum is represented by the symbol L. So as you can see here, this is angular momentum. L is equal to I times omega, where I is the rotational inertia and omega is the angular velocity. So when you have an object that is rotating, angular momentum quantifies the rotation of that body. So essentially, it's just like momentum. Recall that a bullet has lots of momentum and also an elephant, because it's hard to stop them once they start moving. So it's the same as with angular momentum. If an object has lots of angular momentum, then it is very hard to stop that object. So L is I times omega. The units for I is kilogram times meter squared. Therefore, the unit of L is kilogram meter squared per second. Recall that radians is not really a unit, so we can just leave it out. This is the unit, as a unit for angular momentum, kilogram meter squared per second. We have a concept called conservation of angular momentum, as shown here in this ice skater demonstration. So at the start, when he was rotating with arms spread out, the rotation is slow. But when he drew his arms closer, the rotation is faster. And that's because of the concept of conservation of angular momentum. So, angular momentum, which is Li is equal to LF. Conservation angular momentum, which states that the total angular momentum before of an object is equal to the total angular momentum of that object after. So if you expand that equation, we have if we expand on the equation, Li is equal to Lf, we have I sub I omega I is equal to I sub f omega f, which means that the angular momentum. So when the man spread his arms like that, like in my drawing, the distribution of mass of this person from the axis being here, this axis, the distribution of mass is farther away from the axis as he spread his arms. So that means that initially the man has big I, and as we saw, the angular speed is slower, as we saw in the video. Now when the person, after this, or arms are closer together, it means that what he did was he changed his rotational inertia. The person changed his rotational inertia by putting his arms together closer to the axis. In fact, he reduced his rotational inertia. So as you can see, I draw the big I is now smaller. It's a smaller value because the arms are closer to the axis this time around. What happens is, in order to maintain conservation of angular momentum, then the omega has to adjust, and we really can see that the omega also has to increase here. So if the both sides of the equation should still be equal. And we should expect omega to be bigger right now because I is smaller, and that's what we see in real life in ice skate and whatnot.
Good. One more.